Hello students and welcome to the lecture. So students, as we know that we are covering the light and so far we have done with the part 1 and part 2. This is going to be a part 3. I hope you have revised the previous lectures in the well enough manner before you have make yourself available or presented for this particular lecture. Why I'm reminding you again and again? There is a one simple reason that all the parts that we have covered, we are covering and we will cover. All these parts are interrelated to each other. So if you are not revising them on the regular basis, you won't be able to understand the ongoing part and upcoming part in a proper and efficient manner. And that is going to affect you and you only. So that's why I'm asking you kindly revise the facts and figures at all we have discussed in one lecture before you go for the another lecture. Okay, so let's start. Here in this lecture, we are going to talk about the image formation by the spherical mirrors, formulae related to mirror, refraction of light, refraction at plane surface, cause of refraction, laws of refraction, relation between the refractive index and the speed of light, factors affecting the refractive index of medium, the principle of reversibility of path of light, real and apparent depth. So again, let's repeat them. Image and formation by spherical mirrors, formulae related to the mirror, refraction of light, refraction at plane surface, cause of refraction, laws of refraction, relation between the refractive index and the speed of light, factors affecting the refractive index of medium, the principle of reversibility of path of light, real and apparent depth. So these are going to be the point of discussion for us in this particular lecture. But before starting of the actual lecture, as usual, we have the small disclaimer over here that we are required to understood before we proceed further. So the disclaimer is like the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Now, let's begin with the first topic, that is the image formation by spherical mirrors. So if you remember in the previous part, that was light part 2, we had discussed about the spherical mirrors and we had discussed that these are of two types, concave and convex. In concave, the mirror is inward. In convex, the mirror is outward. Right? So here, when we are going to talk about the image formation by the spherical mirrors, so we always considered the both of kind, the concave and the convex. The both kinds will be considered here. So let's check it out. The image formed by a mirror depends on the position of object and nature of mirror. This is an important term, that whatsoever image you will observe by using the spherical mirror, that is actually depend upon, or we could say the formation of that image is actually depends upon the position of object, where the object is placed, and what is the nature of mirror, whether the mirror is concave or convex. So these two things actually defining the image or the outcome that we will observe on the screen. Therefore, the concave or convex, in the nature of mirror, the type of mirror, whatever you want to call it, you can call it. It's totally up to you. Okay. So there is a tabular form, and with this tabular form, we will try to understand that at what position, with which kind of mirror we got which kind of image. Okay. So first case that we are going to see is for the concave mirror. This is. Case 1, position of object, ray diagram, details of the image. So first case, when we put the object at infinity, which means that we have not determined the distance of the object between the mirror, or we can say distance between the object and the mirror. We have not defined it. The object is at infinity. So when the object is at infinity, this will be a ray diagram. Suppose the object is here, then the image is coming, the rays are coming like this, and these images are actually getting converted at focus F. So if we go by the details of the image, first we will get the real image. Why real? Because I have told you in the previous lecture also, if the image is forming before the screen, then the image is real. If the image is forming beyond the screen, that is not real. That is the virtual image. Okay. So here, if you look at here, this is the screen. The image is not forming beyond it. The image is forming before it. So that's why it is a real image. This is inverted, means if the object is in that side, the image will be formed in that side, inverted. And the image is very small. Similarly, you can see it. It is just a dot. Got it? So first case we have seen, when the object will be at infinity, the image will be real, creating before the screen, inverting the position, and the image size will be very small, and that will be at F. Okay. Second case, between infinity and C. So right now we are saying that this is the C. Okay. The object is here. The object is between the infinity and C. So right now we could say we haven't determined the distance the object is placed at. Okay, again I'm saying we haven't determined the distance the object is placed at. But right now we are saying the object is placed at infinity and between the C. Okay, so in such a case, the first ray goes like this and this, the second ray goes like this. And we know in the previous lecture also we had seen when the rays are going parallel to each other, like this case. Okay, if they are going parallel to each other, no image will be formed. But if they intersect each other, so the place where they intersect, the image will be formed. So here you can say that image is going like this and that image is going like, that ray is going like this and that ray is going like this, and here is the point where they are intersecting. So this is the point they are intersecting, so there will be the point the image is. So again we will get a real image. Why? Because the image is forming before the screen, not beyond the screen. Inverted, here you can say by seeing this arrow. So this arrow is in the upward direction, but here you can say the arrow is in downward direction. Okay, so the image is inverted. The image is diminished. Diminished means now here you can say this arrow is larger in size in comparison with this size. Okay, so the object will be larger but the image will be smaller, and the image will be formed between F and C. This is an F, this is C. The image will form between them. Got it? So these two cases we have seen, and these two cases are for concave mirror. Remember it. Now let's move forward. Third case is when we place the object at C. Now the object is at C. Now we have determined the distance between the mirror and the object. So here you can say this is an object, that upward side. This is an object. First ray is going like this, striking the mirror, reflecting like this. Second ray is going like this, striking the mirror, getting reflecting. Okay, so here you can say they are not intersecting each other, so no image will be formed. But This is the point where they are intersecting each other. So here you can say the image will be formed. And what kind of image will be formed? Real, because it is forming before the screen, not beyond the screen. First case. Inverted equal. Now what is the meaning of inverted equal? If you consider the prior to case, in prior to case the image was inverted because the image was real. Okay, that's why the image was inverted. But the image was of smaller size. The object was of larger size, the image was of smaller size. Here, if you look at here, you will find out the height of the object is same as the height of the image. Often we could call it like the size of object is same as size of image. So that's why we are saying it is equal. M equals to -1. And the point where the image will formed at C. At C, the image will be formed. Got it? Now, let's have a look on the fourth case. Now, the object is between F and C. Here, the object is between F and C. So, the first ray going like this, striking the mirror, going like that. Second ray is going like this, striking the mirror and going like this. Again, the image will be formed here because the rays are intersecting each other there. So what kind of image will be formed? First, real image. Why? Before the screen, not beyond the screen. That is the mantra I'm repeating again so that you must be cleared with your concept. If image is forming before the mirror, always real. If the image forming beyond the mirror, always virtual. Okay. Again, inverted because it is real. Enlarged. Now, in this case, the image will be enlarged. Why? If you look at this arrow and if you look at this image size, if you are noticing it, it is quite difficult to notice it, but let me tell you, the image is actually quite in high in comparison with the object. So that's why it is written down, it is enlarged. Or we could say M is greater than -1. The image position will be between C and infinity. It is not like at C. If you look at this image, you will say that they both are at the same. So why we are considering them as a different cases? If the image formation is at the same place, why we are considering them as a different places? Because here the image was forming at C clearly, but here it is between C and infinity. It is not accurately at C. That is the reason why we are considering them as a different cases, why we are not saying that these are the same cases. Got it? So 4 cases we have seen for the concave mirror. Now let's move ahead for concave mirror. Another 2 cases. First, the object is at F. Here you can see. So one ray coming like this, striking and go back. Second ray coming like this, striking and going like this. So here we could say real, inverted, enlarged at infinity. But here you will say, if you look at this diagram, you will find out that no image is actually getting forming here. So how we are saying that the image will be formed like this? Why? You will say that these both lines are parallel to each other. And we just revise, when the rays are parallel to each other, no image could be formed. To image or to forming an image, it is quite necessary that the both lines must be intersecting each other. So let me show you. So if you look at this diagram that I have created for you right now, so you will say these rays are parallel here, but these rays will intersect each other when we stretch them beyond. Okay, so once they intersect with each other, our condition will be satisfied to form an image, right? What we require just to make the rays intersect each other, and here the rays are intersecting. Okay, so the image will be formed. Now just look at the image cases. Again, the image is forming before the mirror, not beyond the mirror. Image will be real. Now, if you look at this object, the arrow is in the upward side. If you look at this image, the arrow is in the downward side. So again, the inverted, enlarged. Now you can say, if you look at this object and if you look at this image size, what you are getting? Is the size of object and image same? Is the size of object is bigger than the image size? No, they both are same. Okay, sorry, they both are different. So the object is smaller, the image size is larger. So enlarge image. M is greater than -1. And remember, the image will be at infinity because we don't know exactly where these both lines will intersect each other. For our convenience, we stretch them, but still we do not know where they will. Okay, so remember, the image will be at infinity. Now, the sixth case, the object is between F and P. Principal focus, F. Now there is an object. Here you can see. So one ray is going like this and second ray is going like this. So even if you stretch them, what you will find out? The distance between them will grow only. They will run up parallel to each other. They will not intersect with each other at all. And if they are not going to intersect with each other, what will happen? No image will be formed. That's it, right? So instead of stretching the lines here, we will stretch the lines there. And after some time, we could say the rays are intersecting with each other. And when the rays got intersecting with each other, that's the moment what we require. The image will be formed. But here, the image will be virtual. Why? If you put all the concept that you have learned here in the one row, that you will get to know that the image is now not forming before the mirror. The image is forming beyond the mirror. Here it is before the mirror. Here it is beyond the mirror. So when the image is forming beyond the mirror, it is virtual always. Erect. Why? Here the image is inverted. The arrow is upward, this arrow is downward. Here the object is in upward direction, the image is also in upward direction. The image will be enlarged. M is greater than +1. Why +1? Because for virtual images we use +1. For real images we use -1. Remember this. And the image will be behind the mirror. Here you can say. Okay. So these are some cases, total 6 cases for the concave mirrors that we have gone through. Now let's have a look image formation by convex spherical mirror. So again, number of cases, position of object, ray diagram, details of the image. First, when the object is at infinity. So for example, the object it is at here. First ray coming like this, striking and go like this. Second ray coming like this, striking and going like this. So here you can say again the rays will be parallel to each other. They will not intersect with each other. And if they will be parallel, again no image will be formed. So what we will do? We will enlarge these rays, and when we do it, here they will intersect with each other. Got it? But here is again a case. Why? The image is not forming before the mirror, forming beyond the mirror. And whenever the image is forming beyond the mirror, it's always a case of virtuality, not reality. Okay, so it will be virtual. That image will be erect because if the object is in upward direction, the image will be also in the upward direction, but the image size will be small, very small. So m will be very shorter than +1, and the formation of the image will be at f. Okay. Now, second case, in front of mirror. Now the object is in front of mirror. Okay. So for this, virtual, erect, diminish, m is lower than +1, image will be between p and f. That will be the case. Got it? So here we had seen the cases. Image formation by spherical mirrors. We have seen the concave mirrors, 6 cases were there. For convex mirrors, 2 cases were there. I have explained you the things, the image formation by showing you the diagrams. I request you kindly revise them and practice them a lot, because the questions comes from them in the examination. And if you are not revising them and practicing them on the regular basis, you won't be able to score that much in your examination. That is a clear cut defined thing. Okay. So now let's see the formulas that are related to the mirror. Formulae related to the mirror. The focal length of a spherical mirror of radius r is given by f equals to r by 2. In R convention, f or r is negative for concave or converging mirror and positive for convex or converging mirror. So this is important point. For R convention, f or r, they always negative for concave or converging mirror. They always positive for convex or converging mirror. The power of a mirror is defined by P equals to minus 1 by F into M equals to minus 100 by FCM. So if the case of meter, we use 1. If the case is of centimeter, we use 100. Okay. So the unit of power is diopter. If the focal length of a converging mirror is 15 centimeter, for example, it's 15 centimeter, its power will be P equals to minus 100 by minus 50 equals to plus 2 diopter. Now here you will see why we are using 2 minus and minus here. Why? Because converging mirror, and we have just read it out here. If the mirror is converging or concave, F or R will always be negative. So here we can say this is F and this is R. So that's why we could say they both will be in negative. So when they both in the negative, negative plus 2D. Got it? If a thin object of linear size O is situated vertically on the axis of a mirror at a distance U from the pole, and its image of size I is formed at a distance V from the pole magnification, then it is defined as M equals to I by O equals to minus A by U. Here, negative magnification implies that the image is inverted with respect to object, while positive magnification means that the image is erect with respect to object. Okay, so if the object is in upward direction and this is the direction of image, that will always be a inverted. Magnification will be negative. Okay, if the object is in upward direction, the image is also in upward direction, that will be a case of positive magnification. Why? Because the image is erect. Here you can see also. Okay, if this is an object upward direction, the image is in downward direction. Negative magnification always, and inverted. If they both in the same, then positive magnification means the image is erect. Thereafter, if an object is placed at a distance u from the pole of a mirror and its image is formed at a distance v, then in such a case, 1 by v plus 1 by u equals to 1 by f. Remember this. In this formula, to calculate unknown and known quantities, are substitute with proper sign. Use of spherical mirrors, if we talk about, so a concave mirror could be used to the following uses. It could be used as a shaving mirror, as a reflector, in torch, searchlight, headlight of automobiles, cars, and cycles, etc. A concave, polished, metallical surface is used as a reflector to obtain a parallel beam of lights. For this, the source of light is placed at a focus of the concave mirror, which act as a reflector. Okay. Thereafter, the rays of light coming from the bulb source of light after reflection from the concave polished metallic surface, which actually acting like a mirror, are obtained in the form of parallel beams. So we could say as a doctor's head mirror that could be used. If a parallel beam of light is incident on a concave mirror, it focuses the beam to a point. This fact enables us to use it as a doctor's head mirror to concentrate light beam on a small area to be examined like nose, throat, ear, teeth, etc. For this, a parallel beam of light is made to fall on the concave mirror attached to the band tied at the forehead of the doctor examining the body part. So, if you ever go to the doctors, mainly like ENT doctors, ear, nose, throat, and dentists and all, you always observe that they wear this kind of thing on their heads. Okay, so basically, this is the concave mirror, this is the light. Sorry, this is the concave mirror and the lights, and this is also a mirror. So here you can say when a parallel light beam is actually fall on this concave mirror, it concentrate this on the one point or the shorter area or smaller area which is to be examined by the doctor. That could be nose, that could be throat, that could be ear, that could be teeth, etc. Any could be there. Okay. For this, a parallel beam of light is made to fall on the concave mirror that is actually attached to the band tied at the forehead of the doctor who is examining the body part. Now let's have a look of what are the uses of concave mirror. A concave mirror is put to the following uses. First, as a reflector in the street lamps. A concave polished metallic surface is used in street lamps as a reflector so as to manage the light over a larger area. Okay, so when the light strikes on this actually spread the light over the large area. So that's why it is used as a reflector. Thereafter, as a rear view of mirror, a convex mirror manages the incident light rays and always forms a virtual, small, and erect image between its poles and the focus. This fact enables the driver to use it as a rear mirror in vehicles to see all the traffic approaching from behind. So it's having a capacity to show a wider area into a wider area into a small screen. So if you are using your car mirror like this, okay, this is your car or vehicle mirror. So here you can say you will see the traffic that is coming behind you. Okay, this is a mirror that is attached to your vehicle. Okay, you can easily see it. Why? Because it is having a capacity to show the wider area into a small place. So it enables the driver to see the traffic that is coming beyond him. Thereafter, the distinction between a plane mirror, concave mirror, and a convex mirror without touching it. Like if you touch the mirror by observing the surface, you could easily say that this is the plane, this is the concave, this is the convex. But if I ask you, I'm showing you the mirrors from some distance, and you are required to tell me whether these mirrors are concave, convex, or plane. So how would you do that? That is the main thing. So to distinguish between a plane mirror, the concave mirror, and a convex mirror, the given mirror is held near the face and the image is seen. So we know all of them, plane, convex, concave, they all form a different kind of pictures because of the formation and reflection of the rays that incidenting on. Okay, so if you held your face near to the mirror and then you see what kind of your image is forming through this mirror, then you could observe it and you could easily tell whether the mirror is plane, concave or convex. There could be the following three cases for them. Case 1, if the image is upright, same size and does not change in size by moving the face towards or away from the face, the mirror is plane. Okay, so like you are standing in front of a mirror, your image that is forming in the mirror is upright, same your size, and whether you are going far and coming close to the mirror, the image is also moving and not changing in size. Then it is a plane mirror. You could easily see this. Second case, if the image is upright but magnified and it becomes inverted on moving the mirror away from the face, the mirror is concave. So if you are standing in front of a mirror, you are looking at your image and you are finding your image is upright but not as your size but magnified. And when you are moving away from the mirror, your image is getting upright to inverted. Then the mirror is concave. Third case, if the image is upright and diminished and it remains upright on moving the mirror away from the face, the mirror is convex. So if you are standing in front of a mirror, you are seeing your image, you are in the upright direction, but not as your size, but diminished. And when you try to move away from the mirror, the image is still the upright image. It's not getting inverted and it's not also moving with you. Then it is a convex mirror. So these three cases are there. First case, when you are standing in front of a mirror, you are seeing your upright image as your same size, moving or coming towards the mirror, the image is also moving. Plane mirror. You are standing in front of a mirror, your image is upright, but not as your size, it is magnified. And when you try to move away from the mirror, your image is inverted, concave mirror. If you are standing in front of a mirror, you are seeing your image upright, but not as your same size, it is diminished. And when you are trying to move away, it is not getting inverted, but remaining as upright, that is the convex mirror. So that's how, without touching the mirror, by seeing the image only, you could tell whether the mirror is plane, concave, or convex. Okay. Now, after this, let's have a talk over the refraction of light. So basically, the change in the direction of path of light when it passes from the transparent medium to another transparent medium is actually what we call a refraction. Okay, so here both the mediums are transparent, so that this phenomena could be observed easily. If any of them is not a transparent, translucent or opaque, then we will not be able to observe this phenomenon. The refraction of light essentially a surface phenomenon that is actually happens because of surface of the two mediums or interaction of the light rays on the surface of two mediums. In figure, this one, the surface separating the two media, saying air and the glass. When light traveling in air falls on the surface, SS dash, a small part of it reflected back in air, obeying the laws of reflection. Rest of it refracted through glass. Therefore, there is partial reflection and partial reflection at the boundary surface. So here this is pencil. When the rays striking and coming down it, some part is reflecting back as the laws of reflection, some part is still there. So here you can say at this point there is a partial refraction and partial reflection. Why? Because this is a glass surface, this is an air surface. Thus the intensity or the amplitude of reflected light is less than of the incident ray. In figure AO represents incident ray, this one. OB is reflected ray, OB, this one, here you can say. OC reflected ray, this one you can say. And NOM is normal, NOM, This one, this entire normal, because here the refracted ray also considering. Angle AON is angle of incident. Angle I and angle BOM is angle of refraction, angle R. The angle I is not equal to angle R. It has been experimentally observed that, now we are talking about the reflection at the plane surface. When a ray of light travels from a rare medium to a denser medium, say from air to glass, it bends toward the normal. Therefore, angle I becomes greater than angle R. When a ray of light travels from a denser to a rare medium, say from glass to air, it bends away from the normal. Therefore, angle I is greater than the angle R. Third, when the ray of light which is incident normally on the surface separating the two media pass undeviated, angle I equals to angle R, both are 0. So here there is a note, but before reading this note, there are the three cases that we could see here. When a ray of light travels from a rare medium to a denser medium, from air to glass, it bends towards the normal. Therefore, here you can say this one. So angle I is becomes greater than the angle of R for the first case. When a ray of light travels from a denser to a rare medium, bends away from the normal. This one, denser to a rare medium. This is a normal. It's actually bends away from it. So here, angle I is smaller than the angle R. And when a case, the ray of light incidentally normally on the surface separating the two media, this like, and passing undeviated. In such a case, both angle I and R equal and they both are 0. There is no work of them because there is no incident observed. There is no reflection observed. Okay. There is an important note. Here, it is worth noting that in case of sound, as V, water, is greater than the velocity of air. Water is rarer than air or for sound. So in passing from air to water, sound wave bends away from the normal while light bends towards the normal. So this is a phenomena that is actually observing in different rares of light and sound. For sound, velocity in water is greater than the velocity in air because water is rarer than in air for sound. But for light, it is not. So when a sound passing from air to water, it bends away from the normal. In case of light, when the light is passing air to water, the light it bends towards the normal. So this is an important case you are required to understand. Now let's have a talk on what are the causes of refraction, why the refraction actually happens. So the refraction of light occurs because light travels with different speeds in different media. Okay. The speed of light is maximum in vacuum and is equal to 3x into 10 power 8 meter seconds power minus 1. In any other transparent media, the speed of light is less than that in air or vacuum. Thus, when a ray of light passes from one medium to the, its speed and wavelength changes, but the frequency and the color and phase of light remains unchanged. So, the sole cause of refraction is actually because the light travels with different speeds in different media. In one media, it's having a different state, another media, different speed, another media, different speeds. Its speed changes with the traveling in mediums. So that's why the refraction happens. For example, the speed of light is actually maximum in vacuum. So whenever the light is travel from the vacuum, speed is maximum. That is equal to the 3 into 10 power 8 meter seconds power minus 1. In any other transparent media, the speed of light is less than that in air or vacuum. So, however, we could say air is also a transparent medium, vacuum is also, but other transparent medium are not air or vacuum where the light having a maximum speed. So that's why the speed of light in these transparent medium, although they are transparent, remains less. So thus, when a ray of light passes from one medium to another, its speed and wavelength changes. Okay. In the beginning of this slide, in the part 1, I have told you this in the clear and cut way. So if you are revising the lectures on the proper basis, you must be aware about it. If you are not, don't worry, just do it. But here you can get a small kind of revision. When light move from one medium to another, from like this medium to this air medium, okay, or this medium to this medium, you can say the speed and wavelength of light will change. But the frequency, and because of the frequency, the color is defined, and the phase of light that will remain unchanged. So that's why we could observe the cause of refraction. Now, what are the laws of refraction? So far, we have seen the cause. Now, what are the laws of refraction? The refraction of light obeys the following two laws of refraction. The incident ray, the refracted ray, and the normal at the point of incident lie in the same plane. The sine of the angle of incident bears a constant ratio with the sine of the angle of refraction for a pair of media. This constant ratio is called the refractive index of the second medium with respect to the first and is generally represented by the Greek letter mu. It is also represented by the letter n. So first let's understand the laws. The first law says the incident ray, the refracted ray, and the normal at the point of incident lie in the same plane. So this is the two surfaces, vacuum and water, lighter, denser. This is the light ray coming, incident ray, then this is the refracted ray. Now you can say they both and the normal also, they are on the same plane. Okay, so first law states that the incident ray, refracted ray, and the normal, they all would be at the same plane. Second case, sine of the angle of incidence bears a constant ratio with the sine of the angle of refraction. So this angle of incidence equals to the angle of refraction for a pair of media. Okay, and this constant ratio is what we call as the refractive index of the second medium with respect to the first. So this is the second medium, this is the first medium. So in respect of this incident angle to the refractive angle, we will calculate the refractive index, like whatever the speed of light was in vacuum in comparison with the speed of light in that particular medium. For example, here is water. If glass will be there, glass will be there. Okay, and this is represented by the Greek letter mu, and also we could use n to represent it. So there is nothing to be get confused that whether should we use mu or n. We could use both. The above law that we have seen is actually called the Snell's law. It is named after the scientist Willibrord Snell, who first formulated it. Here you can see that handsome guy. Okay, he is the Willibrord Snell who first formulated this. So thus, if light travels from air to glass, sine I by sine R equals to mu G. Why we are using mu G? Because G representing the glass, that is the second medium. And always we used second medium in respect to the first medium. Okay, so air is the first medium, glass is second medium. So speed in air by speed in glass, that we will calculate. So that's why we use mu G. Here, mu G is called the reflective index of glass with respect to the air, because glass is the second medium and air is the first medium, and always we use second with the respect to the first. That is what I have told you. However, if the light travels from glass to air with the refractive index of air with respect to the glass is actually denoted by G mu A. Okay, this symbol. Now, what is the relation between the reflective index and the speed of light? The reflective index of a medium is defined as mu equals to the speed of light in vacuum by the speed of light in that particular medium. That medium could be translucent, transparent, water, glass, whatever we could use. Mu is also called the absolute reflective index of the medium. Since reflective index is a pure ratio, it has no units and dimensions. For example, the speed of light in air is 3 into 10 power 8 meters second, powers minus 1. And in glass, it is 2 into 10 power 8 meters seconds, power minus 1. Therefore, the refractive index of glass is mu glass equals to 3 into 10 power 8 by 2 into 10 power 8 equals to 1.5. That's it. We will not put any unit or dimensions before it because it is just a simple and pure ratio. It is nothing more. In general, the refractive index is related to the speed of light in two media as 2 mu 2 equals to the speed of light in medium 1 and the speed of light in medium 2, where 1 mu 2 represents the refractive index of medium 2 with respect to 1. For example, refractive index of glass with respect to water is water mu glass equals to the speed of light in water by speed of light in glass. Notes, refractive index is scalar quantity. It's only having a magnitude, no directions. So that's when it's only a scalar quantity. As in vacuum or free space, the speed of light of all wavelength is maximum and equal to c. So as for all wavelengths, the refractive index of free space is minimum and is mu equals to cv plus cc by cv plus cc equals to 1. So that is important. For what? Vacuum of free space, the speed of light of all wavelength is maximum equals to c. So for all the free space, the minimum is mu equals to cv plus cc equals to 1. That's it. Now, what are the factors that affecting the refractive index of medium? That is what we are required to understand. Like, how does the refractive index of medium affects? Why the speed of light affects? So for a given light, denser is the medium, lesser will be the speed of light, and so greater will be the refractive index. For a given light, denser the medium, lesser will be the speed, and greater will be the refractive index. First thing, example, this is speed in glass is lower than the speed in water. So mu g is higher than mu water. Okay, because glass is more denser than the water. So in glass, the speed of light will be lesser, and when the speed of light will be lesser, automatically the refractive index of glass will be higher. Here V represents the speed of light and mu represents the refractive index. G represents the glass and W represents the water. Therefore, for a given light, refractive index depend on nature of medium. Therefore, mu is directly proportional to 1 by V. For a given medium other than free space, the speed of light of different wavelength is different. Therefore, V is directly proportional to lambda and mu is equals to C by V, and mu is directly proportional to 1 by lambda. Therefore, greater the wavelength of light, lesser will be the refractive index. Second condition, if the light having a greater wavelength or higher wavelength, the refractive index will be low automatically. Example, the lambda R is greater than the lambda B. So in water and glass, the mu of glass is greater than the mu B. Therefore, for a given medium, refractive index depend on the wavelength of that particular light. Actually, mu varies with lambda according to Cauchy relation. Mu equals to A plus B by lambda square, where A and B are constant. There is a note. If the refractive indexes of medium unequal, therefore if mu7 equals to mu2 equals to mu, then the ray passes undeviated from the boundary and the boundary will not be visible. This is also why a transparent solid is invisible in a liquid if mu8 equals to mu liquid. Or you could say if the mu of solid equals to mu liquid, then even you place a transparent solid, that will become invisible. Why? Because the boundaries will not be visible. You won't be able to find out whether there is a transparent solid or not. So according to this principle, Here we are going to talk about the principle of reversibility of path of light. According to this principle, the path of light ray is reversible. In figure, a ray of light AO is incident at an angle I, here you can say, on the plane surface SS, this SS dash, sorry, separating the two media 1 and 2. This is media 1, this is medium 2. It is refracted along OB at angle of refraction R, this one, OB, reflection R. The refractive index of medium 2 with respect to the medium 1 is 1 mu2 equals to sin I by sin R, it's equation 1. Now, if the reaction take place from the medium 2 to 1, the principle of reversibility requires that the ray of light incident along BO at angle of incident R in medium 2 will be reflected along OA at angle of reflection I in medium 1. The refractive index of medium 1 with respect to the medium 2 is then 2 mu1 equals to sin R by sin I. This is the situation 2. From equation N 1 and 2 we could conclude 1 mu2 into 2 mu1 equals to sin I by sin R into sin R by sin I, or 1 mu2 into 2 mu1 equals to 1, or 1 mu2 equals to 1 by 2 mu1, or 2 mu1 equals to 1 by 1 into 1 mu2. Thus, if reflective index of glass with respect to air is A mu g equals to 3 by 2, the reflective index of air with respect to glass 8 mu A will be equal to 2 by 3. Real and apparent path. Now let's have a look on this. An object placed in a denser medium when viewed from a rare medium appears to be at a depth lesser than its real depth. Apparent depth equals to real depth by mu. For a glass, A mu g equals to 3 by 2. Therefore, a glass slab appears to be only 2/3 of its real thickness when it is viewed from vertically above. For water, A mu of water equals to 4 by 3. Therefore, the depth of a water pond appears 3/4 of its real depth on seeing it from the vertically above. It appears shallow. A fish will appear near the water surface than its actual depth. So with this, we have finished this part. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.